Good morning, everyone. Thank you for being here. Oh, I don't know what happened there. I pressed something. Yeah, now it's working. So thank you for being here, and thank you for the people who are online. I appreciate your presence here. And I have some announcements before we start the lecture or resume the lecture that we had the last time. Actually, I have observed that when the class is online, I can see a whole people there. Almost the whole class is online. That's interesting. And that makes sense. That happens all the time on this campus. I guess many people are commuting very long distances and they prefer to be online or something happens, right? That's why I've been teaching online most of the time, this class, because there's a huge demand for online classes. So it makes sense. And driving to Stockholm sometimes is not fun because of the traffic. Depending where you live, if you're coming from East Bay, it's a nightmare. If you come from South, it's a nightmare. If you come from North, it's a nightmare. So it's kind of hard to arrive to Stockton if you live very far. So I understand that. Let me just start with some announcements first. This is my schedule. It might change a little bit. These are the classes that I'm teaching the next semester, the next spring, right? Just in case you want to enroll in a class. Of course, you're taking experimental methods, so of course you don't have to take it again, right? That's good. The other one is Human Development Research Seminar. That's going to be fully online. And there is a master's class that is face-to-face in Turlock. If you want to join the master's class, you can do it because I always record a session like I do here. So I share a link, and if you're interested on more stats in your life, you could just join it, and I can add you to the Canvas shell as well. So if you want a little bit more, and it's not very advanced, to be honest. Why? Well, because this is a class for them. Most of the students in this class are from counseling, so they don't like stats. They hate it. So I try to make it advanced, but I watered down a little bit the advanced part. So it's not like a very strong coffee, more like a water with a little bit of coffee, something like that. So that's what I do in that class there. So it says advanced, but it has just a little bit of advanced components. But that happens towards kind of the middle of the semester. At the beginning, it's very similar to this class because I need to do a refresher of many things. So at the beginning is like 5 sessions of PSYC3000 all condensed, right? And then I jump into more advanced things. So if you want to join that class, of course, you can send me an email and I can add you to that class, of course, if you have time. I know life is busy. And yeah, basically human development is online. So if you want to take it, I would be happy to see you there. And I also have another class in the winter. Let me see if it's here. Here, which is this one, the one that I'm teaching right now, Intro to Psychological Test. So if you want, you can join that one too. Of course, I don't know if you know this, but I'm telling you.
You're gonna do more than just that?
More during the winter?
Yeah.
Oh, only one class.
2025?
Yes,
only one.
Yes, because the winter is only 1 month.
Oh, winter.
Yes.
Winter. Okay.
So yeah, that's why. Yeah, winter then spring. So that's why. So some of my colleagues they teach too during the winter, but it's a lot of work for you as an instructor because it's only 1 month, and the quality of what you can deliver is very low. And so that's why I could do 2, but yeah, I decided just to only 1.
Sorry, I was thinking like next fall, like
fall
2025.
Oh no! During the fall of 2025, I still don't know what I want to teach. I need to discuss that with my colleagues here at Stockton. And so I don't know. Probably I'm going to be teaching again PSYC3000 in another seminar, or I might be teaching a new class like cognitive processes, something that is different for me. And so it could be nice. I don't know. The downside of winter is that it's expensive, right? It's very expensive compared to a normal semester, and it's not covered by any financial aid, right? So that's why it's hard to find students to take the winter. As you can see, I have only 7 right there, right? I need more. But if it's only 7, that's okay. That's fine. And normally, winter classes, many people know they're easy because instructors don't have time to evaluate a lot. So when people are like delayed on their programs, they start saving money to take classes in the winter, so they go faster, right? That's another way to go faster. If you have money to take classes in the winter, so you will finish this program faster.
I have a question about the research seminar.
Yes.
You said it's online, but then it said that there's a lab.
That's wrong.
In person?
Yes, no, that's gonna be online too.
Oh, okay.
Yes, no, I already talked with my boss, and that was a mistake from our administrator, and she's overwhelmed with a lot of work. We need another assistant in our department, so she was like just submitting information, and then she's gonna change it later. Yes, no, that's gonna be online, because given the situation with the new baby that is arriving to my family, I don't think I'm gonna be able to drive here, so it's gonna be only online. Yeah.
Is that the one where you have like group projects and you interact?
Yes, yes, that's the only way.
Is that
Unfortunately.
hard online?
No, it's not hard. That's a very easy seminar. The idea of the seminars is not to make it difficult or easy. It's just like your instructor is like a consultant, and it just guides you through the process of creating your own research, like doing a mini thesis, like a mini micro thesis, for example, something like that. So the research seminars is a good introduction on how you can do a thesis and how to create like a scientific product. So yeah, I mean, and you can take as many as you need, or as many as you have time and money, right? So we have like 4 seminars online many times, or 6. So you can take as many as you need, right? And they all have the same format.
And we can like still set up Zoom meetings with you if we're confused.
Definitely. Actually, that's when I meet the most with people in
Right.
seminars.
Okay.
Yes. Yeah, I talk a lot with people in the seminars. All right. Oh, another thing is that on YouTube, I told you that, let me just go to my probably. Let me see, how can I go there? Well, I've been posting all these videos on YouTube, and I told you that they would be hidden from the search, right? But I enabled them to be public for one reason. It is that one of your classmates has difficulties accessing Canvas sometimes. So I made it public so she can just go there and get access to that videos. And I can delete the videos once that semester is done, if you think that that's okay, or I don't mind having the videos there. I don't see your faces there in the videos anyway, so it should be fine. But if you ever feel like, oh, the video shouldn't be there because my voice is there, or my picture, or my face, just let me know, and I will delete it in December or around January. I can't delete anything from my camera, from my channel, it's fine. But yeah, they're public now, and just because of that. If I don't enable it to be public, if it's hidden from the search and you go to my channel, nobody can see it. Only if you have the link. And the only way to get the link is going to Canvas. But if you have trouble going to Canvas, well, you don't have a second option, right? So that's why I made it public, just to let you know that happened and asking your permission to do that, right? But yeah, you can go here, and I found a way to track the comments. If you want to make a comment on YouTube, you can also do it. I found a way how to track the comments, which is nice. So you can make comments there, like, hey, that's a very old video. No, I don't know. Or nasty comments are good too. No, I'm kidding. Let me see. Any other announcement? That's it. I believe that's it. Yeah. The other day I forgot to do that. All right, perfect. So the last time I told you about this family of models that we're going to study, right? But not all the members will be studying in this class. And let me just probably activate. Should I? Can I do this? Yeah, just in case. I don't know. All right. We can see the chat, just in case somebody is. Right. So I told you that we have a stability test and linear regression, and now we are studying something ANOVA, something called ANOVA. Oh, I don't want that there. Do you need it? All right. That's not what I want. I just wanted to record everything with captions. I don't like that. Probably distracting. It's still there. Hey man, right here. Okay, cool. I thought it would record the text later on. It's fine. This is something that we call the general linear model, right here. And everything is part of the same theory. Everything actually is related to create a linear model, right? I told you that ANOVA will be useful for comparing multiple groups, and similar to regression, right? Regression does the same thing. You can add multiple groups, and you can test if the differences in means are explained by chance or no, right? Or not. In this case, the null hypothesis says that the mean of group 1, group 2, and group 3 are the same, right? That's the null model or the null hypothesis. So we need to find information. We need to find data to see if we can reject the null hypothesis. We might keep it, right? If the result is that we should keep it, it's fine, right? I explained. Well, I took the data set. Let me just click this. How things open here. I told you that we're going to use this data set. Well, this variable from the data set wage, right? So we have the variable is marital status, right? We have 5 groups for this example, and this is the wage of each group, or the average wage for each group, right? And the question that we need to answer is, are the mean differences in wage by marital status explainable by chance, right? By chance alone. And that's when I told you that we can do something like this, right? We have a model and we have error. There is variance explained by the model and variance that you cannot explain by the model. And it's exactly the same logic that the regression model follows. And it's also the same logic that the t-test follows too. Exactly the same thing. It's the same logic behind all these 3 models. What I'm explaining is something that adding a little bit more, but it's exactly the same, right? And of course, ANOVA will use another type of estimation of the line of the perfect fit. And what it does is to estimate a total sum of squares, right? And then it will add the sum of squares for the model, right? So that means that these are 2 different ways to estimate variance. So the first part is estimating the total change, right? And which is not explained by the model. It's just things that are changing. And then you add a model, and that model is the one that will tell you, will help you to estimate how much is not explained by the model and how much is explained by the model, right? And also you have to estimate the other part, which is the residuals. Residuals are pieces of information that we don't know, right? So then you estimate the sum squares of the residuals, and what you would have is, so far, what you have is, for instance, the total, right? That you have a total variability happening there, right? There's a total score for that. Let's imagine that. And then what you have is the model, right? You saw the sum of squares. And actually, you could divide this by the residuals, right? Or the information that you don't know. And in this example, I show you how it looks like in R. I will show you how it looks like in Jamovi as well. Oh, I already did, I don't remember. In here, what we have is the function AOB. I already explained you this. And we have the variable, this variable is our outcome, and this is our predictor, right? Or our independent variable. And actually it looks very similar to a regression model, right? The only difference is the function. We are using the function AOB, but it's exactly the same formula, In this case, I told you that there is difference between groups, right? This p-value is telling me that yes, at least one mean is different from the other in this example, but we don't know which one, right? It's something that we call an omnibus test. So we need to find out which mean is different from the other means, right? That's when I show you this plot, right? This box plot with different scores for each group. And I told you that this group is the group that has the highest wage, right, in this data set, which is people who are married. And never married is also high compared to the other three that are widow, divorced, or separated, right? So we did, well, I show you how to do this. Let me just, this is the code for doing this. Actually, I should remove this space right here. What I did was to run this function, Toki AHD. I will explain you more about it later. But what I did was a pairwise comparison. So I was comparing married versus never married, widow versus never married, and this is the mean difference. It's just a subtraction in this column, right? And here you can see the p-value. And of course, the mean difference between married and never married is very big and is not explained by chance, according to the p-value, which is way less than 0.00, way less than 0.05, right? And you can see it right here, right? Right here, you see there is a big gap between this mean and this mean. So yeah, of course, married people are reporting a higher wage. We already know that. And we already saw that the differences between these three groups are explained by chance because the p-value, well, not this one. Let me just delete this part. Not this one. It's actually this one. And this guy. Yeah. All these ones are explained by chance because the p-value is way larger than 0.05, right? And those means are these ones. In the last part, we're comparing this versus this versus this, and this guy versus, well, this group versus this group. And of course, visually, you can tell that they are not actually different, right? The wage for these three groups is very similar, and they don't have a lot of outliers. Only one here and not here. We have more outliers in these groups right here, right? People earning a lot of money, people who have never been married, getting a lot of money, and people who are married also getting a lot of money here, right? Like $300 or more. But there are exceptions; they are not the rule, right? Oh, and a few married people at the bottom, right here. You know, poor guys. They struggle, for sure. They struggle. All right. I told you that in the t-test, we use the t-distribution to find out the probability of finding an estimate as extreme as the one that you got, right, from your data, right? And what we do is to check the area under the curve. So we check the area under the curve, and we check the probability of finding any estimate. And of course, the t-test is called the t-test because we use the t-distribution. In ANOVA, we are going to use the F distribution. And this F distribution will have degrees of freedom. We will have one number that is going to be the numerator, and the other number is going to be called the denominator. It's like a fraction. And an F distribution can look like this, right? It's bounded at 0, and it has positive values, and many times it has a very long tail here. And most of the distribution is going to be located, most of the density for the distribution will be located around these kind of numbers. It depends on, of course, on the degrees of freedom, right? And actually, the last time, let me see if I have it open here. No, close it. Let me just go here 1 second. And the last time, I show you that you can change the values. These two values, these 5 and 10, they are degrees of freedom. And these will control the shape of your distribution. So I show you that when you have very big degrees of freedom, let me make it smaller. Otherwise, it will not display the plot. Yeah, there we go. So it starts to look more like a normal-ish distribution, right? Actually, that distribution could look like a normal distribution depending on the degrees of freedom. In the case of the ANOVA, we are gonna estimate those degrees of freedom out of the model. You don't have to know the degrees of freedom. There is a formula to estimate the degrees of freedom in your test, and we will see it. Remember that we were estimating the sum of the squares of the model and the sum of the squares of the residuals. Now, we are going to use that information, and we are going to divide that by the degrees of freedom of the model. And how do we estimate that? Well, there is a rule of thumb for that. So for the degrees of freedom of my model, I just need to take the number of groups and subtract 1. So in this case, in this example, we have 5 groups, and I just subtracted 1. That will give you the degrees of freedom of the model. And then you need the degrees of freedom of the residuals. And normally you take the sample size and you subtract the number of groups from the sample size. And of course, this is going to be a big degrees of freedom. And actually, you can see the degrees of freedom right here in this table, the same table that I showed before. You look at this column right here, and this will tell you the degrees of freedom of the model and the degrees of freedom for the residuals. So these degrees of freedom will help you to estimate the p-value. You will see it later. As I said, you don't have to kind of guess the degrees of freedom. Just following these rules of thumb, you will get the degrees of freedom for your model and the degrees of freedom for your residuals. And after doing that, you will get something called the F ratio or the F value, similar to the T value. Instead of a T value, we are going to call it F value because it is F distributed, right? So this value here it's a value that is commonly generated by the F distribution. So now that we have that value, we can actually see where it's located under the curve. of the F distribution, but not any F distribution. An F distribution with these degrees of freedom. That's why we need the estimation of the degrees of freedom. Because you need to know under what specifically distribution of F values is the model located, right? Because you can have infinite numbers of F distributions in the universe. I mean, if you modify each of the degrees of freedom, it will give you thousands of combinations of possible F values. But you don't need any F distribution. You need the F distribution that belongs to the model, right? That is part of the model. That is going to be the distribution for your model. So that's why in this case, oh, wait, I don't know what happens. Yeah, now it works. So now, under those degrees of freedom, I can check how extreme is my estimate. And the estimate is very extreme. It's located right here, right? It's right here. It is close to zero, as you can see here, right? So it's a very extreme value. That value is not explained by chance. Everything that is here would be explained by chance, right? Because this is my null model with an F distribution. But in this case, of course, it's very extreme. So that's why the p-value is a very tiny number, which is right here. This number right here. It is 0.0016 zeros, and at the end, there's a number 2. So it's a very tiny number, right? So tiny that it's better to use scientific notation, because otherwise it would be a lot of zeros, and it's boring to see a lot of zeros. So that means that it's quantifying this probability, right? So the probability of finding these F ratios is very tiny, right? So, and you can see the F value right here. This is the F value that I calculated by hand in these steps right here, right? So at the end, what we do is this, look at this. We take the mean square of my model divided by the mean square of my residuals. It's just a ratio. So it is the amount of variability that my model explains divided by the amount of variability that I cannot explain. It's just a proportion. It's just that. And that proportion will give you a F value right here, right? Now, let me check if I have another example here. Right here. F. So, for example, let's imagine that you want to calculate this number by hand, right? Well, not by hand, you can use R. You can use the function that I'm providing here. It says PF. It stands for probability of F, right? So let's imagine that you don't have the p-value. You could estimate the p-value by just adding the F value from the table, which is 55.96. And that should give you no, yes, false. There's some rounding error. But yeah, it's a very tiny number, right? So you can use this function to estimate what is the value, what is the probability of your F value. And that's what actually R is doing behind the scenes. It's just using the probability density function of the F distribution. So remember, in here, the value that we are testing is not even the differences of each mean. right? This value is actually like a transformation from the information from the model in the residuals. So that's why we don't know which mean is different. That's why we call it the omnibus test or overall test. It's just telling us, yes, there is a difference, but we don't know where, right? In regression, it's different. In regression, you can see the difference from a reference group right away. You don't need an omnibus test in regression. You just see the difference between the reference group and the target groups, right? Which is kind of nice. That's why I prefer many times regression instead of doing ANOVA. But if you do ANOVA or regression, you will arrive to the same conclusion. Okay, as always, we will have assumptions. All the time we have assumptions, right? And in ANOVA, we have assumptions, and they are exactly similar to the ones that you have in regression and test. And one of them is the constant variance. The variance of all the groups are the same. That's one of the assumptions. And remember, the assumptions belong to the model, not to the data. The data is what it is. What we are testing is if the model is a good model to explain the data. Always remember that, right? We are not testing if the data is good to explain the model. That would be like cheating, scientific cheating, right? The data was produced by nature. What we are testing is if our model is good or not, right? If it has a good fit according to our needs, right? So the assumptions are about the model, not about the data. So what it means is that we are assuming that in nature, all the variance, all these 5 groups are the same. That's what we are assuming. Well, we need to test that assumption because we don't know. It might be the case that this model is not good for my data because the variances cannot be assumed to be equal or constant among all the groups, right? How do we test that? Well, there is something called the Levin's test. Exactly the same test that you would do in the case of the t-test. Remember that in the t-test, we can also test, a lot of tests in that sentence. Well, we can evaluate if the variance is equal between groups or not, right? And we use that test right there, the Levin's test. You can also use it in Jamovi. In any software, actually, in SPSS or any other software. That's another thing. If you take seminars with another instructor, that instructor might use another software. He or she might use SPSS, and I'm not using SPSS. So if that happens, send me an email. I can still help you if your instructor doesn't have time in the future. Of course, just send me emails. I'm always there, and I always will help you. So yeah, SPSS, for example, will do exactly the same. It has some clicks, and you click, and you will be able to test if the variance is the same or not between groups. Now, how do we read this? In the Levin's test, the null hypothesis is that all the variances are the same between groups. So this is the null. Let's call this V for variance and sub-zero right here. So we are assuming that the variance 1 is equal to variance 2 and is equal, well, actually, no, let's change it for H. I don't like here because it's confusing. Let's use H, that stands for hypothesis right here. And the variance of root 3 is going to be the same, and so on, right? Let's do ... right here. So the null hypothesis in the Levin's test says that all these variances are the same, right? When the p-value is less than 0.05, that means that we cannot hold this assumption. We cannot hold this hypothesis. Because the p-value is telling us that, hey, no, the null hypothesis cannot be held in this case. So in this in this model, the variances are not the same between groups, right? Which is kind of bad. That means that there is something that we call heterogeneity. And it's not bad. I mean, in terms of good or bad, like, oh, it's a bad model or bad data. It's just it's not the correct model for the problem. And I will show you the plot again of this data, and you will see why I say that. But yeah, probably is not the best model because we cannot assume that the variances are the same, right? There are corrections for that as always. You could actually do another ANOVA that is corrected by the fact that the variances are not the same. But still, it's just an approximation of a good model. Ah, look at that. I already said that here. Nice. Always remember to pay attention to these boxes. They're very important. Now, I'm saying something here. Actually, this is a note to myself. I should tell you this. And this is right. There is another thing or another characteristic in this data. The problem is that we have 3,000 observations in this data set. It's a lot of observations. So this t-test could tell you that the p-value is less than 0.05 because you have a lot of power to detect any difference. So when you have a large sample size, p-values are useless. Why? Because when you are swimming in data, the p-value will always be less than 0.005, even if the correlation is very small. Like for example, let's imagine that you have a correlation of 0.00005, right? It's a very small correlation. But you have 10,000 observations. That correlation could be significant just because you have 10,000 observations, right? So that's something that is called overpowered. It's a test that is overpowered. So the p-value is useless. You cannot use p-values. You have to do other things, other ways to make decisions, right? Or you can split the data, or you can do different types of models. There are things that you can do. But trust that p-value, when you have a lot of data, and it's something that probably you don't want to do. So in this case, I haven't tested, I haven't done any sensitivity analysis on this because, it's a lecture and I don't want to overcomplicate a lot of things. But you could actually do a sensitivity analysis and see if you are kind of overpowered here. But probably we are. So I don't know. It could happen. But yes, 3,000 people is a lot for this test. In here, what I did was to plot, let me see here, yes, was to plot the predicted values of wage and the residuals of wage, right? And how I did it? Well, what I did was a regression model, which is going to be very similar to an O. It's exactly the same. And look at what's happening here. In fact, yeah, I wouldn't say that the variance is the same across all groups because there is a lot of variability here. These dots are very far from here, and these guys right here, and look at this group right here, which is the married people. I didn't create variable labels here. I should change these to create labels, but this is the married people, and as you can see, there's a lot of variability here. So the variance in these groups is clearly not the same, right? If you see the plot, when you plot your predicted values in the residuals, yeah, they don't look very good. So probably a linear regression model is not the best for this data. And we already know that, right? And you remember when I did like a curve on this data, right? So a non-linear model is probably better. We can do the same. We can do similar plots. But in this case, I'm using just the absolute value of the residuals, right? Remember, residuals could be negative and positive. So residuals is the distance from the line of perfect fit. So some people might be below the line of perfect fit, and they would have negative values. Or they could be above the line of perfect fit, and they would have positive values. In the previous plot, I had negative and positive residuals, and actually you can see it here. Let me show you. Right? In this y-axis, look at this. We have negative and positive. But you can also do the same with absolute values. Remember that an absolute number is just a number that will be positive all the time, right? And in here, you can see the same pattern, right? It's another way to see the same pattern if you want to. And it's exactly the same story. Look at the dots, all those dots there. If the change in each group was similar, all these circles that are right there should be kind of packed together with the other ones, but they are not there. So that means that the variability is not homogeneous. It is heterogeneous, right? And to be honest, that happens all the time with income and SES status, right? With many of the variables that you measure for SES, this will happen. And it depends on how big is the gap between each social-economical class in different countries, right? In the United States, unfortunately, the gap is very big compared to other countries. So the gap between the middle class and the high class is huge. So that means that the middle class has problems to ever go up a little bit, right? The United States is less equal compared to other countries, like, for example, Norway, Finland, they have a better chance to go up in the ladder, right? The United States is not like that. It's hard. It's way harder than other countries. Well, these developed countries, or whatever developed countries are, I don't know. So this is not surprising. Actually, if my friends from economics would be here, they would say, yeah, that makes sense. You're not telling something different from what we already know. Well, actually, it would work. We don't know. I don't know why. Yes. Well. So this is another way to check assumptions. And in here, I'm using a linear regression model. But it actually would work with ANOVA. I just need to add a continuous predictor. I don't know why I said that. Well, it's fine. Don't pay attention to this part, because it should work with ANOVA too. At least in R. It will not work in Jamovi, but it will work in R. Well, yeah, this example is with a linear regression model. In here, I did a regression of worry predicting anxiety. Right? We already know about this relationship. And what I did was to plot the predicted values of anxiety and the residuals of my model. I'm going to explain you more about predicted values later. What do I mean? What do I mean about predicted? What I mean is that once you have a model, I probably can explain you this. Once you have a model, like for example, this one, beta sub 0 plus beta sub 1, x 1 here, plus error, right? Once you have this, and then you estimate the model, right? Let's imagine that you have values for this beta, right? You estimate a model. So beta is not beta anymore. Beta is actual a number, it's an estimated number. So let's imagine that the beta is 50 plus beta 1 is not unknown anymore if you estimate a model like we do here. So let's imagine that your slope, I don't know, could be 10. And x is our observed variable. So you could multiply this by any value. So let's imagine that, I don't know, I have Lila's anxiety score here. So her score is 50 because she's anxious all the time. I don't know. And then I can, well, actually with this, I can estimate a slope. So now I have information to plug in where X was located. And I also have the estimated value for the slope and the estimated value for the intercept. So that's why we have equations. And that's why we estimate data. We have data to estimate these equations. You can replace the X, the beta, and the beta sub 1 and beta sub 0 by a number. And then the result is the predicted value. The predicted value for Lila, who had a score of 50. But I can add any number there. I can add your number, I can add your anxiety score, and get a predicted value, a prediction for you, right? So that's how we also are able to predict scores for people who are not in this data set. I can predict the anxiety score for your, I don't know, for your husband, for your partner, whoever you think should be in this data, but it's not here. You could predict that value following the model that you estimated, right? Of course. That's why we need a better model. In this case, I have only one predictor, which is X. Well, X of 1, right? But I need another predictor. Instead of anxiety, it could be depression, it could be SES, socioeconomic status, it could be your academic level. So that's why, in order to get good predictions, we need good models. And good models need very good sources of information and very good variables in the equation, right? Variables that make sense and variables that are related with the outcome. Otherwise, it's useless, right? So when I say predicted, I'm doing that. Well, R is doing it for me. What R is doing is taking the values that I have in the data set, and it plugs in the values into the equation, into X. And it gives me a predicted value for each individual in my data set. But as I said, it could be any other value. It could be values for another data set, from another future, from anywhere, right? Because remember, models will always produce data. That's the whole point. So in this plot, what I did was that, right? I got predicted values for the anxiety score, and I got the residuals, the pieces of information that I cannot explain with my model. And look at how it looks like. You can evaluate the constant variance using this scatter plot. So in this case, the variance is not constant at all, right? If the variance was constant, these dots would be like spread out across this line. They wouldn't be so high right here or so low right here. And these people right here wouldn't be that extreme, right? So the variability here is not actually constant. It changes, right? Another way to see non-homogeneous data is by looking at clusters. Sometimes these plots will display, let me just, how can I, right here. Sometimes these plots will actually look like this. So remember, in this case, X is going to be predicted values. I'm going to call it P for predicted. And Y is going to be our residuals, right? I'm going to call it R. So many times these plots, there is a line at 0. It's kind of useful because the mean is 0, the residuals. This is standardized residuals. So sometimes the dots might look like in clusters. Like some dots are here, then other group is here, right? Even though the variable is continuous, it shows like clusters, like groups together. And that's something that we need to address in the model, because that means that the data is not constant, the variance is not constant, right? The variance is different by each value of X. So that shouldn't be happening if we want to do a linear model, right? If you want to estimate a linear model. So in this case, of course, ANOVA regression or t-test would be useless because they cannot explain the variability that we are seeing, right? And when that happens, we use something called random effects models, or some people call it multi-level models, for example. So that means that the data is nested into different clusters, and we need to do something about it. But as always, that's kind of an advanced topic. I'm not going to ask you to do that in this class. But I'm just telling you how the data could look like in your research projects. Another way to another way to test the assumption of let me see. Yes, the assumption of equality of variances is by doing something called the Gleichzerr test. And this test is not visual. All the things that we saw is kind of a visual tool to examine your data, right? Examine your assumption. But you could do tests or evaluations on that with a p-value. We always do that. And one of them is this one. So in this case, what we are going to do is use the predicted values, y hat. What I haven't explained you this. I need to modify these slides. When you see y and a little hat over y, that means predicted values. So if I do something like this in a slide or in statistics, like for example, I do a number here, right? And then I do 10 by 5, and you see this y hat on the other end, it means that I'm getting predicted values out of a model. So we call it y hat. That's how we call predicted values in regression. So in this slide right here, I call my predictor y hat. And my outcome is going to be the residuals of the model. So in other words, I'm regressing this x on these residuals right here, right? I'm explaining the residuals by my predicted values, which is weird, right? So you'll be thinking, well, that's kind of weird. So what is the conclusion here? Well, what we are evaluating is if my residuals are constant. If my residuals are constant, that means that I can hold the assumption of equality of variances, because my residuals are the best proxy that I have to that statement. It's the best that we can do. We don't have the exact error, right? We cannot have the exact error of the model because the error is something that happens in nature. Of course, you could get multiple samples and multiple samples and multiple samples, and you will be closer to that error. But still, you will be a little bit far. But the only thing that we have, the best that we have is residuals, and we can explain the residuals by using the predicted model, the predicted values, right? And what is the conclusion here? Well, the conclusion here is that we would have a slope. And if this slope is not explained by chance, like in this case, right, the p-value is very small, that means that the variance is not constant. And we already know that by looking at the plot that we saw before, right? We saw that, look at that, it's everywhere, variance is everywhere, the variability is changing, right? There is not exactly a good pattern. And actually the test is telling us the same. If this p-value was larger than 0.05, I could hold the assumption of constant variance. I could just say, yes, yeah, I have evidence that the variance is constant. But in this case, it was not, right? This is another way you can test if the variance is constant or not, if you can hold the assumption, right? And actually, this is a little bit better compared to the Levin's test. The Levin's test is way more biased because of the sample size. This one could be a little bit better. And you can create plots of your residuals. which is very important. Now, let's talk about normality, but probably we need to take a break before we start that. Let's come back at 11:05. That's okay. Take a break, and we will be right back. All right, let's continue with this. I believe we're gonna finish early today anyway, which is fine. So I can address some questions if you have questions for practices and assignments. Remember that we also have a assumption of normality in regression, right? Remember that I told you that that we assume that the distribution that best explains the conditional distribution of y given x is a normal distribution or Gaussian distribution. It's the same assumption for ANOVA. It's exactly the same. ANOVA has the same assumption. It will assume that the best distribution for reflecting the differences between groups is a normal distribution. But I didn't tell you how to test that. How you actually test if the normal distribution is the best model for your data, right? We don't know. So there's two ways to do it. One way is using graphs. So in this case, let me see what I did. I don't remember. What is that? Yes. This is a regression model of worry, predicting anxiety, right? And what I did was to take the theoretical quantiles of the normal distribution. Remember that we can use any quantile from any continuous distribution and plot the observed quantiles versus the theoretical quantile, because we have the formula for that. We have the probability density function for each of the probability distributions in the universe, or the ones that we already know, right? We have the formula for that. So we are able just to plot the theoretical quantiles. And in this case, things don't look good. This is something that we call the normal QQ plot, right? Or quantile plot. And things don't look very good here for this model. Look at these observations right here. These people right here, right? And look at these people right here. And look at these people right here. So these students here, or these participants, they are more normalish. Why? Because they lay down across the line of perfect fit. So these people actually, this model is good for these people, but it's very bad for these people right here. The model cannot explain how these guys were produced because they are far from the line of perfect fit in this case. And these guys too, right? They are off at the line right here. It's like we have three clusters. It's like we have people with high score, people with like a average score, and they are actually very good explained by this model, and people with very low score. And let me see if I have an example here of a perfect fit. Oh no, I don't have it here. Well, so when the data was produced by a normal distribution, these dots should be all laying down on this line of perfect fit, but they don't, right? So the problem is, yeah, probably a linear model is not the best model to explain the relationship between worry and anxiety. And in psychopathology, that also makes sense sometimes. Because if somebody is very high on a psychopathological trait, right, that person cannot be explained with a normal distribution. Those people are very far from the mean. So what happens with the normal distribution? The normal distribution tries to push everyone towards the mean. That's why we call it normal. We want them to be normal. But in psychopathology, they couldn't be called normal in the sense that their symptoms are way off, right? So that's why they're in treatment. That's why they need help, right? So of course, the normal distribution probably is not the best model for them, right? And in here, in this data, I have some people who are very high compared to the average in this data set, and that's why the model is telling 8. This is the best I can do. Probably a nonlinear model would be better because the nonlinear model would actually explain all these guys here. I didn't try, actually, I should try. I don't know if I have the data there. So yeah, probably a nonlinear model would be better for this type of plot. Now, that's one way to evaluate normality. So the conclusion from that plot is no. The normal distribution is not the best model for my data. That's the conclusion. Therefore, the regression model, the linear regression model, probably is not the best model for my data. Right? But sometimes the plot can be confusing. So we don't trust the plot. We trust a test, like the Shapiro-Wilk normality test. I don't like it, to be honest. I prefer to evaluate everything visually, because if you have a large sample size, that test will tell you that the normal distribution is not the best for your data, right? Because you will be overpowered. And that's why I prefer many times just to take a look at the plots. But some people still trust the p-value from this test, and that's okay. And your instructors in different levels in this program will use actually the Shapiro-Wilk normality test. That's why I teach this one. And in this test, the null hypothesis says that the distribution of my residuals comes from a normal distribution. So the distribution of my residuals from my model are normally distributed. That's the null hypothesis. The alternative hypothesis says that they are not produced by the normal distribution. So in this case, the p-value is very small. It is a number that it has 12 zeros, 0.00000, and at the end you will find 1612, right? It's a very, very tiny number. It's telling you that we need to reject the null. If the p-value is less than 0.05, we reject the null hypothesis. Therefore, the residuals are not explained by a normal distribution. They were not generated by a normal distribution. So that means that we cannot hold the assumption of normality for ANOVA or regression. We can't, right? In this case. And we will need to find another model for this data. Probably a model that will allow for nonlinear relationships is better, and actually many times it is better. Especially because we are talking about anxiety and worry, and probably the tendency is not linear, right? Probably there is a point where if you worry a lot, your anxiety doesn't increase. It kind of keeps stable over time. It doesn't change, probably. So that's why the linear model is not the best. But actually, we could do an exercise. One of the practices with that, it would be fun. So find the best model for this data. Well, at least for this relationship. Now, things to remark in this test. Remember that I told you in one of our lectures, I don't know if you remember, probably not, that's okay. You are not the analyst, you are just there. But I mentioned in one of my lectures that many people believe that the predictors of the regression should be normally distributed. Many people wrongly believe that. Other people wrongly believe that the dependent variable should be normally distributed in the case of the regression model, or in the case of the ANOVA, which is wrong. These models are not assuming anything about the distribution of your outcome or your predictors. It is assuming something about the conditional relationship of y given x, which is different. So how do we evaluate the conditional distribution of y given x? By analyzing the residuals of my model. That's the best proxy that we have for testing that assumption. That's the best option that we have. So that's why in this test, I just estimated the residuals from the model. I just got it. I mean, the model already produced the residuals, right? The model will tell you, this is what I can explain, and this is the part that I can't. But if I use the residuals, they are a good indicator of the relationship between y and given x. So we test the assumption of normality on the residuals because they are the product of our conditional distribution of y given x. We don't test the distribution. We don't test if the distribution or the values of my independent variables by itself were produced by a normal distribution, right? Or my outcome. It doesn't matter, right? It doesn't matter if the outcome was not produced by a normal distribution, right? So never test your normality assumption on your individual variables. You have to test it in the model by getting the residuals, right? That's very important. And that's something that happens all the time at all levels in academia, especially in social sciences. Even some of your professors probably told you to do this in your outcome or in your predictors, right? And which is wrong. Do it in the residuals. Do it, just extract the residuals. The good thing is that Jamovi, for example, will do it for you. You don't have to get the residuals. In R, you have to. We will do both ways in different assignments and practice. We are running a little bit out of time for more assignments, but I want to squeeze more, a little bit more of assignments very soon. I need you to have more practice on doing several things. And some of the assignments are going to be repetitions, like similar steps to the ones that you did before, but it's going to be a different data set. Why I like repetition? Because repetition helps to understand what you're doing little by little. If you do the same thing all over again, you kind of get more practice on what you're doing. So it's going to be like a repetition. It's going to be boring because it's going to be the same thing. But we're going to repeat the steps that you need to understand in order to be successful in this program. And probably beyond this one in a master's, if you do a master's or a PhD. Oh, and let me show you here. Oh, I didn't show here probably in these slides. Look at this. This is how I got the residuals from my model. What I did was to use the object PSYC3000Oct22Fall2024, which is my regression. And then with $sign, you can get access to the residuals right here. I will explain more later in a video, but this is how you get the residuals in R from your regression object, right? This is my regression object. And this is how, if you type $sign residuals, you get the residuals out of the model, out of the object.
Can you remind me, what does the $sign do again? Like why?
Yes, that's very important. The $sign is more like an at.
Okay.
So it's like, get me the residuals at this object.
Okay.
That's what it means. Yes, it's weird that they don't use at, but we use at in another type of object in R. Actually, it's used in another type of object, is the S4 object, not the S3 object. But in this type of method, we don't use at, we use $sign. Yeah. All right, let me just jump into Jamovi 1 second so I can show you how it looks like. Oh, it opened two. Wait, give me one. Let me see if I have wage. Yeah, wage is right here. So if you want to do a ANOVA, you can go to the module that says ANOVA right here. Very convenient, right? You can also download this data from a web page if you are using a computer right now or any other device. You can go to my web page and download a wage data set if you want to. If not, it's fine. So in here, we are going to use the function, well, the module one-way ANOVA right here. And you will see this beautiful interface. And in here, when I say beautiful, those kind of things, I sound like Bob Ross a lot. Yeah, it's the influence of Bob Ross on me. So in here, on grouping variable, you need to add a nominal variable, right? Nominal means that you have labels, right? Groups. If you add a continuous variable here, the program will tell you, hey, I don't know what to do with this because it's continuous, right? So in this case, we can do a ANOVA with education, right? Education has multiple groups. And then the dependent variable could be wage. And let's see what happens. You don't have to click or anything. It will automatically generate the ANOVA analysis. And in this case, it's telling me that the mean of wage by educational level or education level is not explained by chance, right? The differences observed are not explained by chance, but we don't know which means, right? I don't know. So if we want to get the mean differences, we need to check, for example, the gain-whole unique variances under the tab post-hoc. And let's see what happens. It will give you this kind of tidy table. It looks like a correlation table, but it's not a correlation table. They decided to display the information like this. I mean, it's something that the programmers decided. It's not something that you have to do, but they decided this was the best way to display the information. So in here, what we see is the mean difference between people who have high school versus people who have less than high school, right? Who probably had some years of high school, but they dropped from high school. And that mean difference is not explained by chance. Actually, the people who dropped high school are getting minus $11.7 less, right? It makes sense. If you drop high school, the salary that you can get is not going to be the best. Unless you're some sort of genius that you created something and then you got a lot of money. Tell me.
Are those data sets that you have?
They
I don't have them in mind, so how's that gonna?
Oh, no. I will give you the data sets, the assignments, but if you want them right now.
No.
No? Oh, okay.
Maybe, I don't know.
They're here. No, let me just tell you. Well, other people might have the same question.
Okay.
Let me just show you here. If you go to the website, msquared.net, and then you go to experimental methods and designs, it's right here.
Oh.
Data sets used in this course, and then you can download from here. Just in case, right? All right. So let's check more these mean differences. Another thing that is happening here is that we are comparing less than high school with some college, right? People who finished high school, they went to college, they didn't finish college, they drop out from college, right? And they are actually, people who drop from high school are getting $23.7 less compared to people who had some college. And the tendency continues, look at that. If you have a college graduate degree, you are getting $40 more compared to a person who didn't finish high school, right? And if you have an advanced degree, you are getting $66 more, or 67 if you round it, more compared to people who didn't finish high school, right? So of course, this means that what we already know, if you study more, your salary is going to be better, right? People are telling lies. Some people are dropping education just because they believe that they're going to have a better life, but that's not true. We still need education. We still need to attend classes, and we still need to learn something. And let's see what happens with, for example, college graduate versus advanced degree. The difference is also big, right? If you have only college degree or college graduate, you are getting $26, well, $27 rounded, less compared to advanced degree. And that difference is not explained by chance, right? Because the p-value is less than 0.005. Jamovi will not show the exact number because it's a very, very tiny number. So it will just create these labels that says less than, meaning that it's telling you that this number is, the p-value here is way less than 0.001, right? It's a very tiny number. And let's see if we can find differences that are explained by chance. No, all the differences are not explained by chance. Everything that you can see is less than 0.005, right? And perfect. Now, we need to check assumptions. Remember that. I went ahead and I analyzed the data, but you shouldn't do that. First, you need to check your assumptions. So how do you do that in Jamovi? Well, there is a box, well, a section that says assumption checks. Look at that. That's why we love this software for teaching, because it's like locating sections and you can see, right? So you can test the homogeneity of variances, or if the variance is constant across all groups. And look at that, it's using the Levin's test, the same one that I told you before. And look at what it's telling us. The p-value is less than 0.005. That means that we need to reject the null. The variances in each group are not the same. They are different. So we cannot hold the assumption of equality of variances. That's kind of bad, because that means that the linear model probably is not the best for this data. The model that we are running is not the best for this model. That's why when you do a post hoc, which is the comparison between groups, you should check Games-Howell. Look at that, it says unequal variances. So that's one way kind of correct a little bit by the fact that the variances are not the same. It kind of does a good job, but still it's not the best model, right? If you click here on Games-Howell, right, you are assuming that the variances are not equal, right? And that's okay, right? You can do that. But you have to select this option, Games-Howell or Tukey, after conducting your assumption check, right? Before you didn't know. Well, I knew because I know this data, but before you didn't know. So that's why you need to check your assumptions first. Now, in Jamovi, you can click on normality test, and another box will appear. And this is the Shapiro-Wilk test that I mentioned as well in one of my slides today. So the null hypothesis says that the residuals are produced by a normal distribution. That's the null hypothesis. In this case, we need to reject the null because the p-value is less than 0.05. So the residuals of my model are not explained by a normal distribution. That means that it cannot hold the assumption of normality. And again, another bad thing about this model is not the best for this data, right? It's not explaining the data better. These assumptions don't fit into the data. So we need to find another model. And you can check the QQ plot. This is the quantile plot, or the normality quantile plot. On the x-axis, they are plotting the theoretical quantiles, in this case, the quantiles from the normal distribution. And these are the residuals, the standardized residuals from my model, right? And look at these guys right here, right? Again, very extreme cases. We already know that. In this data, there is a gap, a big gap between the mortals and the people who are getting a lot of money, right? So that's producing that this test is telling you, yeah, this data was not produced by normal distribution. Definitely not. Because the normal distribution cannot explain those cases, right? It's another model, probably the best one. Other things that you can do here, for example, you can generate descriptive blocks by clicking here. And this will, this happens because the label is too big for each group. But this is a tiny box plot for each of the groups. And you can see the mean in this circle here. And this is the people with advanced degree, the upper degree in this data set. And of course, they're getting a lot of money, right? And this is the people that had only less than high school, right? Dropout high schools. They are here. And as you can see, if you go up in the academic level, you're getting more money, right? And you can also generate a descriptive table. And that one is going to be at the beginning, I believe, right here. Here you can see the mean of each group by clicking descriptive table right here. And yeah, look at this. The high school, less than high school is getting $84.1. And the people who are in the advanced degree group are getting $150, well, almost 151 on average, right? So yeah, if you study more in this data set, I guess that's what this data set is telling us, you're getting more money. And remember, these are just males. They are not females, so I don't know. This might be different from females, right? I need to find a better data set for this like topic, you know. I cannot make conclusions for females. And I cannot make conclusions for other ethnic groups because they classify the ethnic groups in a very weird way. So it's hard to see kind of the gap by ethnicity and also by gender. There's a big gap, right? When you're a minority in this country, things are tough, right? So yeah, I think that's not reflected very well in this data. And other things. Let me see. I don't remember what was this. This results in this freedom. What? I don't think it changed. I don't know what this option is doing. Oh, right here. Yeah. I know what it's doing. It's just giving us the degrees of freedom and the t-value. Yeah. Because what we are doing is a t-test of each independent mean, or each pair of means, right? That's what it's doing. But you don't need to know. You don't need that information. Other thing that you can do in Jamovi is to click on flag right here. And look at that. It will tell you with the stars the mean differences that are not explained by chance. So it will impose a flag on the mean differences that are not explained by chance, right? Which is kind of nice. Oh, and I forgot to tell you. In the ANOVA section, you can always account for models that don't assume equal variances. So similar to a t-test, you can do a Welch adjustment, as it says here. And if your assumptions check says that the variances are not the same, you should use this option. But if the variances are the same between groups, you can just trust the other option that says Fishers, right? Assume equal variances, Fishers, right? But both in this case are arriving to the same conclusion. So it doesn't matter which one you pick. If by mistake you are reporting the wrong one, to be honest, in this case, it wouldn't matter because it's the same conclusion, right? The differences between groups are not explained by chance. And when you check each pair of means, all the combinations, all the pairwise comparisons are not explained by chance as well, right? And let me see. We might do a repeated measures ANOVA later. And ANCOA is just a regression with more covariables. We will do something about it. And we are not gonna do a MANCOA right here. And if we have time, I can explain non-parametrics, but I don't think we have time for non-parametrics. Well, let's see how it goes. Questions so far about this? Kind of okay? Yeah, cool. So well, let's finish here and watch for the practices and assignments. And to be honest, we already finished all the material that I always teach in this class, you know, and we're really fast here. So the next sections probably are going to be dedicated to new topics, and I'm going to invest more time on assignments. Nothing could be useful for learning more. So probably I'm going to solve some assignments here and practices in class, along with some new content that you will see. And actually, I might overlap practices. Look, the assignments might happen will be like a small lecture for you to read with more explanation on other topics that we need to cover. So you will see it there, right? And thank you. Thank you for your patience as always. Thank you for being here and enjoy the rest of the day. Thank you.
Can I have you show me something?
Yes, of course. And let me just pause the recording. Okay.